In this video, we're going to try and find dy by dx of a polar curve. So cast your mind back from our section on parametric equations. We spent several videos in trying to understand why dy by dx is simply this thing divided by this thing. So you might have to track back to some of the earlier videos to try and understand this. But just a quick reminder, with parametric equations, time would be the driver of everything. So the minute you know time, then you will know this coordinate, you will know this coordinate. So the minute you know time, you can work out the physical x distance, and the minute you know time, then you know the physical y distance. And then if you know the physical y distance and physical x distance, then you can work out dy by dx. So with polar coordinates, it's pretty much the same. You see, theta is the driver of everything. The minute you know theta, you know the precise location of this point. The minute you know up here, the minute you know time, then you know the physical x distance, you know the physical y distance. It's the same thing with polar in polar form. The minute you know the angle, then you know the physical x distance, which is this thing here, and you know the physical y distance, which is this thing here. So if you look at this, let's look at it as an example. Let's say r is given by some function of theta. So when you see r equals some function of theta, what is meant by that is, for example, 1 plus cos 2 theta. You see, here you're given a radius as a function of theta, as a function of theta. So when you come to read this, it is a function of theta. So this is just an example. So at the moment, let's just look at this example. R equals this thing here. Now, the minute you've been given this, then you know the physical x distance. Well, the physical x distance would be you putting this thing into here, and then so the physical x distance here would be 1 plus cos 2 theta, and then times this thing here, cos theta. So the point here is that up here, time's the driver of everything. The minute you know time, you would know the x distance. The minute you know time, then you know the y distance. And if you know the x distance and you know the y distance, then you can work out dy by dx. So down here, the minute you know the angle, then you know the radius, because the minute you know the angle, then you immediately know the radius. Now the minute you know the radius, then you can work out the x distance by using this. And the minute you know the radius, then you know the y distance by using this. So here you know the x distance, and then you know the y distance, because the angle is the driver of everything. So no matter no matter what angle you're given, you will know the x distance, you will know the y distance. So up here, because we're trying to find dy by dx. The minute we know the y distance, the minute we know the x distance, then we can work out dy by dx. Just simply by following this. Differentiate the y with respect to your driver, if you like. In this case, it's the time. Down there it was theta. Your driver was theta. So the minute you know the y distance, the minute you know the x distance, then you can work out dy by dx. You simply differentiate the y. You simply differentiate the up and down here with respect to your driver. Here's time. Down here it was theta. And then you divide it by x. You differentiate the x with respect to your driver. In this case, it's time. Down here is theta. So hang on, going back to here. The minute you know the y distance, the minute you know the x distance, then to work out dy by dx, then you simply follow this. Get this divided by this. So what that means is you differentiate the y. You differentiate the y with respect to your driver. In this case, it's theta. So if you look at this, if you differentiate this, hang on. So here we're trying to differentiate y with respect to theta. Here we're trying to differentiate y with respect to theta. So we've got to differentiate this. So when you differentiate this, remember r is a function of theta, because as you vary theta, as you vary, remember our polar form could be something like this. The minute you vary theta, then r reacts accordingly. So r is a function of theta. R is a function of theta. R is a function of theta. So when you differentiate this, you've got to use implicit differentiation here, because r is a function of theta. And then, so this here, you've got to use a product rule. You got to use a product rule on this. It's like me giving you this. It's like me giving you this. Yx equals 7. Now, y is a function of x. So here you've got to use implicit differentiation. So you got to use a product rule. So you differentiate this. Differentiate y would be 1, but because y is a function of x, then you've got to stick in dy by dx, and then you leave the x alone. You leave the x alone, and then you plus. Now you leave the y alone, and then you differentiate x, which is 1, and then differentiate this, which will be 0, and so on. You use the same. So to differentiate this, you've got to use a product rule, because r is a function of theta, because r reacts to wherever the angle may be. The radius of your circle changes depending on where the radius. So the radius changes depending on where the angle, what the angle will be. So r reacts to the angle. So r is a function of theta. So here you've got to use a product rule. So to use a product rule, so you differentiate this, which will be 1, but because r is a function of theta, then you've got to stick dr by d theta, which is this bit here, You leave this the same, so this is us using the product rule. And then the second part would be plus, and then you leave the radius alone, and then you differentiate this. So that will then give you this. Now, following this, we need to differentiate x with respect to theta. So looking at this, remember r is a function of theta. So we would have to use a product rule on this. So the product rule would be differentiate this, leave this the same. So differentiate that, leave this the same, and then you plus. You plus. Hang on, let me do it properly. Sorry. So let's try and differentiate this. So differentiating this, we've got to use a product rule. So differentiate this would be differentiate this would be 1, and then because r is a function of theta, we will need to stick dr by d theta, and then we've got to leave this the same, which will be cos theta, which is this thing here, and then you plus. Now you leave this the same, and then you differentiate this, which will be minus sine theta, and then this goes out, and then that will give you this. So dy by dx is given by this. This looks ugly when you come to actually do the problem. Don't bother memorizing this. Just do it. This looks scary, but if you try and do a few examples, it's actually quite straightforward. So just bear in mind that if you want to know dy by dx, it would be this. But don't memorize this. Just do it. So just know that you differentiate this, but just bear in mind that you've got to use the product rule here. And then you differentiate this. Just know that you've got to use the product rule here. Don't try to memorize this. Just actually physically do it. I'll give you an example, and then you see what I mean in the next video. Okay.